3.3, parallel and perpendicular lines, day 2. I know yesterday 3.3 was titled a little differently, but it was still day 1. Today is September 30th. Oh, it's not that late yet. Okay, so September 30th, 2020. And you do have an extra word in your objective, so I apologize for that. To apply complex reasoning to complete a 2-column proof to prove lines parallel or perpendicular. It's mostly going to be proving them parallel. There's a couple that we know can prove them perpendicular. One is the definition, and then we're going to look at a second one today. So just so that you have all these in the same place, you don't have to go hunting them down. We're going to review what makes lines parallel or what proves lines parallel. So the first one is a postulate. If the corresponding angles are congruent, then we can prove the lines parallel. B, if the alternate interior angles are congruent, then we can prove the lines parallel. C, if the alternate exterior angles are congruent, then we can prove the lines parallel. If the consecutive interior angles are supplementary, then the lines are parallel. If 2 lines are parallel to the same line, and I'm going to underline that. If 2 lines are parallel to the same line, then they're going to be parallel to each other. And F, if 2 lines are perpendicular to the same line, then they can be proven parallel to each other. Okay. So G is not really proving anything about lines. It's just something we already know, and I wanted to remind you. If 2 lines are perpendicular, then they form 4 right angles. That is not the definition of perpendicular. That is not proving that the lines are parallel. It's that if they're already proven perpendicular, then we know the result is 4. Okay, so H is another way to show that lines are perpendicular. Because until this lesson, the only way to prove 2 lines were perpendicular is by the definition. If there was one right angle, that was the only way you could prove the lines were perpendicular. So how else can you do it? So if 2 lines are already parallel, and we have a transversal that happens to be perpendicular to one of them, then it is going to be perpendicular to the other. I know you don't have a lot of space for this picture, but try to put it in there off to the right. I don't know what I was thinking. Sometimes I do that. I'm like, oh, that's plenty of room. Then it's not. Okay. So line L and line M here are already parallel. Line N is the transversal, and it happens to be perpendicular to L. If it's perpendicular to L, then by using corresponding angles, that means the angle at the bottom is also right. So it's perpendicular to M as well. So in writing, it looks like this. If line L is parallel to line M, and you also know that line N is perpendicular to L, then N also has to be perpendicular to M. So this is the only other way that we have to prove that lines are perpendicular. Everything else is parallel. So let's review, how do you do a proof? Because the basic foundation of a proof is the same no matter if you're proving things about angles and segments, which we did in chapter 2, or if we prove things about lines, which we're doing in chapter 3. It is the same format. So the first thing you're going to do is you're going to write down the given information. Now you can separate them or you can keep them together. I tend to separate them if they're unrelated. Then I'm going to build the information from the given. So what else do you know about the given? Remember, if then, if then, if then. You can only say it's true if you have a postulate, a theorem, a definition, or a property to back you up. Remember, you're citing your sources, and those sources are those postulates, theorems, definitions, or properties. Now, if you have exhausted everything you can say and you're like, but I'm not done, then you might want to go look for a second given, or maybe there's something from the diagram. Remember, if it comes from the diagram, it is going to be a postulate or a definition. So like the angle addition postulate, the segment addition postulate, the definition of vertical angles. You've written down the second given, or you've taken something from the diagram. You want to keep building from there, just as if you started the proof all over again. It's like a restart. At that point, you're like, okay, I can't keep going, but I'm not done. Look if you can combine anything. So the fifth thing you're going to do is you're going to see if you can combine something else. Generally, that's a property like the substitution property or the transitive property, or it's a theorem like congruence of angles is transitive. After you've combined them, generally you can't go much further, but you might be able to by simply going to the proof. So if you have nothing else to say, you've written every given, you've written every logical statement, you've combined everything, where else is there to go? Well, it's to write the proof. So after nothing else can be stated or combined, you should be to what you are trying to prove. And remember that when you get to the bottom, you do not write given, because they didn't give it to you. They just told you where you were going. Okay, so here is our first complete the two-column proof. So anything we've learned up to now is fair game. Chapter 2, Chapter 3, any part of Chapter 3. Again, I would highly recommend you try the if-then trick. Try not to get caught up on definition of, or trying to think that, hey, something has a title. Think about it in the if-then context and you'll probably get farther. So let's start with the question. The question is, given line G is parallel to line H, and you will notice they've already marked that in the diagram. They have also told us that angle 1 is congruent to angle 2. So I'm going to add that to the diagram just so that I have it to help me out. So everything has already been marked in the diagram at this point. So anything else I pull from the diagram has to come from a definition or a postulate. Now in the end, we're supposed to prove that angle 3 and angle 2 have the same measure. You can see that my two givens are unrelated. One is about lines and the other is about angles. So I'm going to separate them. Step 1, angle G is parallel to line H because it was given to me. I didn't make that up, they gave it to me. Number 2, angle 1 is congruent to angle 3. So look at your picture, look at angle 1, look at angle 3. And you will notice that they are in corresponding location. So we want to try the if-then trick. If, then. Okay. So if what? Well, we had two lines that were parallel. So if two lines are parallel, you can say if parallel lines are cut by a transversal. I'm just trying to shorten it because you don't have a lot of space. So if two lines are parallel, don't say then the angles are congruent. Well, which angles? Angle 1 and 3 are corresponding angles. So if two lines are parallel, then the corresponding angles are congruent. And that is from the beginning of the week. So then we're going to get to number 3. Angle 1 and angle 2 are congruent. Okay, so we were just talking about angles 1 and 3. And now we're talking about angles 1 and 2. Like, where did that come from? Remember, there were two separate givens, so I am now writing down the second given. Angle 1 is congruent to angle 2. So number 4, angle 3 is congruent to angle 2. Well, when was the last time we talked about angle 3? Well, it was up here in step 2. When was the last time we talked about angle 2? In a different step, in step 3. So how did they come together? They came together because they are both congruent to angle 1. So you could write in if-then form, if two angles are congruent to the same angle, then they are congruent to each other. However, we've never had a theorem that said that. You could write it and I would take it, but the theorem was congruence of angles is transitive. Congruence of angles is transitive. Okay. Step 5. We are still talking about angle 3 and angle 2. Still talking about them, but now we're talking about them in a different way. So that means that we're back to an if-then. Because we're talking about the same things in a different way. So what happened? We had two angles that were congruent. So if two angles are congruent, then their measures are equal. That happens to be the definition of congruent angles. So you can write it either way, if-then or definition of congruent angles. But you want to be really careful because not everything is a definition and people tend to get overly confident about their definitions. Step 6. Wait a minute. I'm still talking about angles 2 and 3. I'm even still talking about the measures of angles 2 and 3. So I'm going from a measure to a measure. If I go from a measure to a measure, as long as it stays a measure, it's a property. So which property says if two things are equal, they're still equal if you flip them? That is the symmetric property. That is the symmetric property. Go ahead and pause the video if you need to get caught up. And we're going on to example B. And this little thing is in my way. Get that out of the way. Complete a 2-column proof. And this time we're actually going to prove one of our theorems. Because remember, a theorem is a shortcut, but it had to be proven by somebody. So we're going to do what mathematicians did back in the day. We're going to prove the theorem that says if two sides of adjacent acute angles are perpendicular, then the angles are complementary. Now that's not a theorem we've learned, but it's one that exists. It's not used a ton, but it's a great example of practicing a proof. Okay. So they are telling us up front that line EF and line ED are perpendicular. I know they look like rays, but remember they would be lines. In the end, we want to prove that angles 7 and 8 are complementary. So line EF is perpendicular to line ED was given. Now, what do you know about perpendicular lines? You know that perpendicular lines form 4 right angles. You also know that perpendicular lines are made by a right angle. So in this case, since they're only mentioning one angle, you totally can choose. It's up to you. But again, if you try the if-then trick, it makes it easier. If two lines are perpendicular, because that's what we have. We have 2 lines that were perpendicular, then they form a right angle. And if you choose a right angle, then you can write definition of perpendicular lines. But if you were someone who chose 4 right angles, you cannot say it's a definition. In this case, it really doesn't matter which one you use. So what do you know about right angles? Oh, I know they have a measure of 90 degrees. So look, we've started our if, then, over. And how do I know that? Because for one, I'm trying not to concentrate too much on the specifics. I'm trying to think about the generals. What do I know about a right angle? I know it's 90 degrees. Then I look at the proof and go, oh, look, I'm still talking about angle DEF. I'm still talking about it. I'm just talking about it in a different way. So those two still go together. And I'm going to do my if-then trick. If an angle is a right angle, that's what was happening in number 2, then its measure is 90 degrees, or the definition of a right angle. So I wrote the given, and then I kind of ran with it, and I got 2 statements out of it. Then I get to step 4. Great, I'm still talking about the measure of angle DEF. Perfect. But where did angles 7 and 8 come from? Like, they weren't in the proof. So remember, if it's not in the proof yet, it's either another given, which there is not a second given, or it came from the diagram. And that's exactly what happened here. What tells me that 2 smaller adjacent angles can add up to the overall angle? 2 smaller angles, measures, add up to the whole thing. That's the angle addition postulate from way back in chapter 1. Step 5. Well, I'm still talking about the measure of angle 7 and the measure of angle 8, but the measure of angle DEF has disappeared. It's gone. It somehow morphed into 90 degrees. How did it do that? Well, let's go back and look up here. In step 3, the measure of angle DEF was 90 degrees. So I just replaced it. What tells me I can do replacements in a measure? It's the substitution property. And again, how do I know it's a property? Because I went from a measure to a measure to a measure. Measure, 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 measure. That's a property. So it's the substitution property. And finally, number 6, I'm still talking about angle 7 and angle 8, but I'm talking about it in a different way. So I'm going to try my if-then trick. Same thing, but in a different way. I'm going to try my if-then trick. So if 2 angles measures have a sum of 90 degrees, I don't know what's happening on my screen, then they are complementary, otherwise known as the definition of complementary angles. So if you remember in chapter 2 in the helpful hints list, I presented to you that if you're going from a measure to a word, it tends to be a definition. Not always, but it tends to be a definition. So go ahead and pause the video and join us on example C. Our last example says complete the 2-column proof. Line L, sorry, I don't even know where line L came from. Sorry about that. Line N and line M are parallel, so I'm just going to mark it in the diagram so I can see it. And angle 2 is congruent to angle 3. I am just putting that in the diagram so I can see it. So again, I have 2 pieces of given information. They are completely unrelated. One is about a segment and one is about an angle. So I am going to choose to separate them. I'm going to start with the first one. Line N is parallel to line M because it was given. What do you know about parallel lines? From the beginning of the week, we learned that if lines were parallel, things were going to happen to the angles. So if you look, that's exactly what happened. In step 1, we had parallel lines, and in step 2, we had something about the angles. Oh gosh, no, we didn't. Because are angles 2 and 3 on lines M and N? No. So this one kind of throws you off. It seems that it should be if step 1, then step 2, but angles 2 and 3 aren't related to lines M and N. So where did they come from? Remember, we had 2 separate givens. So step 2 is a given as well. So you just really need to watch what's going on. Okay, so then we think about Tuesday's lesson. If 2 angles are congruent, what do you know about some lines? Well, those lines would probably be parallel. So let's look to see if that's really the case. So angles 2 and 3 are on lines N and Q. So this is where your if then is going to occur. But remember, you can't just say if the angles are congruent. You have to tell me specifically what kind. So when you look at lines N and Q, angles 2 and 3 are interior. So if the alternate interior angles are congruent, then the lines are parallel. And then number 4, is talking about parallel lines again. But in step 3, there weren't any angles. So where can step 4 come from? So let's review. In chapter 2, I told you the last step is always going to come from the step above it. But it may come from the step above it and other stuff. So we know that step 4 is going to come from step 3. How do I know that? Well, when was the last time we talked about line Q? In step 3. That was the last time we talked about line Q. When was the last time we talked about line M? The last time we talked about line M was way up in step 1. So how do these get related? Well, here, let me remove some of the stuff that I'm covering up with, and you can see it. Line M is parallel to line N in step 1, and in step 3, line Q is also parallel to line N. So we have a theorem that says if 2 lines are parallel to the same line, then they are parallel to each other. So you want to make sure that you have out that list of helpful hints. I know there was one in chapter 2. Hopefully you found the one for chapter 3, and you are using that as your helpful hints. If you have any questions, please ask your teachers. Don't forget you have a quiz tomorrow on chapter 3, and then we have fall break.